So hello, everyone. Thank you, Alex, for an introduction. So this panel is on creativity, and I'm very happy to be moderating this because I think creativity is very important, and I'm happy to have many creative pioneers, actually, on this panel. So in means of introducing yourself, guys, can you please share your creative approach to cultured meat and also share how you got the inspiration for this?
Hello, this is Yoon. I started research like neuroscience and some DNTP regulation and all those kind of stuff. And I joined the SeaWith as a researcher, but now I'm doing more of the business side of the work. So what we do in SeaWith is a lot of people ask, like, so you guys do seafood, but we are the cultivated beef company. And instead of using regular available scaffold or media, we try to make everything our own. So, you know, everyone knows scaffold in pharma grade is really expensive. So that's made out of alginate, a lot of them. So we got the idea of making straight from the brown algae, and then we extract the gel from the brown algae the way we developed. And then we're just using that, and then all the primary cell that we get grows really well on the scaffold that we do, and that's one of the scaffold side of it. Media-wise, we use microalgae extraction, which will be replacing FPS, and we've been succeeded up to 90 to 95% replacement of the FPS just with the extraction. And then we also developing our own bioreactor for differentiation, since we are using whole cut like a scaffold, which will need a specialized bioreactor. So we have some collaborator to develop our own bioreactor. We have a prototype, but it has to be modified and then developed as for larger scale size of the bioreactor. Yeah, thank you.
Hi, I'm Natalie. I did my PhD at Tufts University in tissue engineering for cultured meat, and then I joined Biotech in January. And our creative approach to cultured meat is just really focusing on scalability. The company was founded to just really unlock scale. As Justin mentioned yesterday, there's just like not enough bioreactor capacity on Earth to, meaningfully make cultured meat at any meaningful scale. So we were founded to rethink bioreactor design from scratch with an emphasis on making them more scalable, lower cost from CapEx and OpEx, and really importantly, specifically fit for purpose for cultured meat rather than pharma. So we're exclusively focused on the cultured meat space and making really, really large bioreactors.
Hi, I'm Deniz. I'm the co-founder and CEO of Prolific Machines. So I don't think that there's one creative approach that is necessary. I think there's a stack of technologies that's going to be necessary to create meat that is affordable, delicious, and nutritious. So I think the question is like, what's the right stack of technologies? And we think about this as a four-part problem. So the first is you have to eliminate the most expensive parts of the media, so recombinant proteins and growth factors, and Prolific has a way of doing that. The second is you have to optimize metabolism and make sure that your carbon that you're putting in is getting put to good use. Prolific has a way of doing that. It really boils down to how well can you control your cells. The third is creating structure, because people don't want to buy mush for the most part. And creating structure is hard, and the way that people have been doing it is mainly retrospective structure, where you have, fat cells in one vat and muscle cells in another vat, and then you kind of put it in a 3D printer and you put it all together and you hope that tastes good. But that's not how structure is created in the body. So we're trying to think about ways to recapitulate how structure is created in the body of an animal, which is, stem cells co-differentiating into different lineages at the same place at the same time. And we think that that is how you create structure with texture that actually recapitulates real meat. So we're working on a solution for that. And then the fourth is something that we're not working on right now, but we're going to be working on in the coming years. And I'm also very interested in collaborating with people like Natalie, which is reducing CapEx costs, because obviously the majority of CapEx in this industry is spent on reactors that were designed for the pharmaceutical industry, which will need to be rethought, because the pharmaceutical industry is super high margin, and you obviously can't apply that same technology to cultured meat and expect to compete with factory farming. So super excited about what ARC are doing. So yeah, those are the 4 things.
Okay, little question on that. So do I understand correctly that you guys are doing co-cultures in bioreactors, or are you guys exploring the options?
So I think it's going to be a 2-part process. There's the proliferation phase, which will be just a single stem cell, and then a second phase where you do the co-differentiation from a single stem cell into multiple different lineages in a separate reactor or separate piece of hardware that we're developing.
Okay, thank you.
I am Jordan Jones. I'm a PhD candidate at WPI. I'm also a visiting scholar at Boston College. And my research surrounds the creation of structured meat products like steak. And like was mentioned, that's very difficult. So our creative approach to solving that problem is using decellularized plant scaffolds, particularly leaves. And what we do is we take advantage of the native vasculature of the leaves, because the plant itself has to solve this exact problem with its tissue. So we take advantage of that, and that's kind of one of our ways of, I guess, being bio-inspired, And essentially what we do is we cannulate the stems of leaves and we perfuse it with media, and the idea is that you culture thick layers of tissue on the surface of the leaf. You can kind of layer them together, kind of like a cake. And that's kind of our approach to generating structured meat products.
All right, thank you guys. So you are all working on your different ways of producing the cultured meat, but after all, in the end, we all have to scale up, of course. So how do you envision this on a much larger scale if you really want to get the whole world to eat cultured meat? I think this question is for all of you again.
So scale up, that's the toughest question. I don't think anyone, probably there's only a few companies thinking about scaling up at this point, they're making their facility and everything. Right now we are still at the benchtop scale. We are pretty small scale-wise, but we are collaborating with a bioreactor company and then automation factory company that will make all the automation part of it. Not only the machine-wise, software-wise, it has to be controlled. All the sensors has to be placed in the right place and the right, with the right options. So not only, I don't think we'll be able to do it ourselves, SeaWith itself. So we have a collaboration with the, I think we came up with yesterday with the Black and Bitch. So I was saying, large corporate will be the big help on that. So we have some collaborators with large corporate who are in food industry, and that's going to help us on step on the large scale part.
Yeah, for ARC, definitely scale up has been at the center of our conversations from day one. So the first time I kind of sat down with our CEO and CTO, we were talking about what the industrial size production facility would look like, and not just an abstract, conversation about what would be cool, but really practical things that I had never thought about, like the capacity limits of shipping containers and different layers of software architecture for automation. So I think just having the right people around the table from day one is really important. Our CTO just has such extensive experience with really large-scale production. So defining certain constraints based on what the end process needs to look like, and then working backwards. So we've had to be more intentional about scaling down, because we've always imagined, what things need to look like at large scale. So just putting those constraints in place from day one has been really helpful, and I think helped us have a different approach. I think we've seen other groups take the approach of okay, we can do this at 1 liter. What do we need to put in place to get that at 10 liters? And just only thinking about the next level of scale, or maybe 2 levels of scale. But it gets just what you need at an industrial sized facility is completely different. So being more intentional about that, I think, is important. And then we also rely heavily on computational modeling tools. That's where, half hardware, half software company. So computational fluid dynamics and digital twin bioreactor technology are really critical to our process to not just, work with automation, but also really ease scale up. So instead of going from 1 liter to 10 liter to 100 to 1,000 to 10,000, these tools will enable us to go and help our customers go from 10 liters to 10,000 plus liters, because the robustness of these tools can actually, really do that and recapitulate what cells, how cells behave in culture.
That really resonates with me, by the way. So Prolific's currently building pilot manufacturing to go up to 1,000 liters, which is still very small relative to what we'll ultimately need to be doing. A question that we spend a lot of time thinking about is what's the minimum volume at which you can build an accurate model of a really large reactor, say 100,000 liter plus. And once you know what that minimum volume is, what's the path to get there as quickly and as cheaply as possible? So that's our scale-up plan, is to build the pilot manufacturing facility up to 1,000 liters, use that to build a model to predict at what volume can we be producing meat on a per unit profitability basis, and then go out and build that manufacturing facility.
So our scale-up approach is, if we look at it from the scaffold side of things, we're looking at mass producing the scaffolds by utilizing somewhat of a vat kind of system. So essentially, you can put large amounts of leaf material, not specifically spinach. I use spinach particularly because it's a good test bed, but in theory, you can use any or a number of different leaves for our process, and you could use the same type of system to mass produce these scaffolds. But on the tissue side of things, we've also been experimenting with other types of plants, and particularly broccoli florets. So that's actually the work of one of my colleagues, Richard Thyden, who's also a PhD candidate at AUPI. And essentially, he plans to use these broccoli florets as a microcarrier of sorts, and so that you can grow the satellite cells in a vat-style system as well, in a stir tank bioreactor. So that's another way that we plan to scale up the process. We've also looked into other microcarrier candidates. Can't really go into much more detail than that, but you get the idea. Essentially, we're focused on mass producing the scaffold itself, as well as being able to facilitate mass proliferation of the satellite cells that we use. So.
All right, thank you. And regarding scaling up, I want to touch upon sterility, because we all know sterility in cell culture is very important, and on a small scale, it's quite easy to do that. But on a larger scale, that will be harder, definitely, if you want to keep the costs down. So this is a question for Natalie and Deniz, like how do you think we should handle this on a larger scale?
Yeah. I'll give the ARC answer and then a more fun, creative answer from my PhD. So I think there's a lot of things we can do to increase sterility. Closed seed trains, so from when you thaw a vial of cells all the way to harvest, basically the cells never see the light of day and have the potential to be contaminated. That involves also like eliminating offline sampling. And definitely just also creating better, cheaper, quicker methods of sterilization. So there's some interesting novel methods of sterilization that I think could be really effective. My fun answer, since this is a panel on creativity, basically we need all these aseptic techniques, right? Because cell culture doesn't have an immune system. But what if it did have its own immune system? I worked with insect cells for my PhD, and insect cells are super fascinating for a number of reasons. Kind of late into my program, I read a paper that says insect cells actually synthesize antimicrobial peptides. So maybe they could just...
Really?
Yeah,
Wow.
and kind of anecdotally, people have noticed that they just don't get contaminated as frequently, and I've actually seen contamination, like I thought my culture was going to get contaminated, and a couple days later it was gone, which was really fascinating. I didn't really look to see if these peptides were being synthesized, but I think it's a really interesting future project, just an example of maybe thinking outside of the box.
Yeah. Yeah, I really like your fun answer. But actually, was wondering if you can give a little bit more details on the ARC answer, actually, where you say that we have like a closed seed train. How would you do that from the beginning of starting the cells all the way to the end?
Yeah, exactly. Can't give like too much information, but basically automation is a big part of the answer.
So you probably wouldn't expand the cells in 2D first, but you would go like straight into a bioreactor, small size, and then go bigger and bigger.
Yeah,
and bigger.
definitely.
Okay. Yeah. Thank you. Thanks.
So this is a really important question. Just to frame the problem for those of you who have never done cell culture, a bacteria divides roughly every 2 hours, and a mammalian cell divides roughly every 24 to 48 hours. And so even if you have one bacteria in your culture, it will rapidly outcompete your mammalian cells. So this is an important problem. I'm glad we're talking about it. I think Prolific has a fundamental advantage here in that we have less inputs. So we have a way of eliminating the growth factors and recombinant proteins, not just replacing them with a cheaper alternative, but getting rid of them entirely. And if you do that, you're essentially reducing the total number of inputs into your culture. And every input that you can eliminate eliminates a source of contamination, especially with proteins, because the easiest way to sterilize something is heat sterilization. But with a protein, you can't do heat sterilization, because if you heat it up, you'll denature it. And so reducing the inputs, I think, is the best way to eliminate contamination or minimize the risk of contamination.
And how would we reduce the inputs?
Oh. My lawyers would be very upset if I answered that question.
Yeah, we'll leave that in the middle then.
But we can talk offline.
We can all talk offline. You can find them later. So I want to touch upon our cell sourcing, actually. So every cultured meat company, every academic lab is using their own cells and isolating them themselves from tissue samples that they get. But that means that we're all actually kind of using different cells. Do you guys think we should regulate this in the future? And if yes, how? And anyone can answer that.
Not only do I think we should, I think there's no choice. Because, the cells that I use, I isolate them myself. And I've tried doing a number of different species, cow, pig, and different types of fish, and they don't behave the same. That being in mind, that being the case, I have to alter the process for each different species, and they all yield different outcomes and different quality of cells. So the question becomes then, like you said, how do we kind of regulate this? And I think the best way to do that is to kind of have, I don't know if you have to create like a profile of what the ideal satellite cell has to be. So maybe if you're talking beef, for instance, you have to come up with the ideal proteome for what a satellite cell is, right? To be used for consumption anyway, because research versus consumption will be very different things, and other industries are regulated in that way too. So I think things like maybe a defined proteome, defined genome, things of that sort, particularly when it comes to differentiation of these satellite cells into the muscle that will be consumed. I think all these things have to be well defined.
Yeah, I think that's a good answer. I have a slightly different answer. At ARC, like data and data quality is really important. So I think more about, rather than like what is done or what cells are used, just like that we have consistent characterization processes and some standards around that. Because, people calculate like doubling time in different ways. And when you need to like input really consistent data into a tool that can be helpful, it's really important that things are consistent and accurate and precise. So I think standards are really important. I think standards could be like kind of defining what a muscle cell is or should be, but also just really detailed protocols for how we characterize our cells. And also just, not where they come from, but how they're treated and how they're isolated and what's done with the cells. Every, thing you do to a cell when you're developing your cell line really impacts how it behaves. So just more documentation and characterization and some centralized place for defining how we do that could be helpful.
I agree with the characterization. The way we approach in SeaWith is kind of unique to Korea. Korean version of FDA is MFDS. They strictly say no GMO, nothing cannot be GMO related. So we can immortalize a cell, or so therefore we use primary cell line. So we extract tissue from the cow and then separate it, and then we make the master bank and working bank and all that. The way we do it is like we have a veterinarian collaboration. So whenever they go out in the field and they get the sample, and we are getting same muscle, same spot, all the time. We have so far about 30 different cells from 30 different animals. So we have to characterize every single cell line that we have. So therefore, we are growing them up to 20, 25 passages, see how they react. And some of them it's really hard because it's 30 different animals. Some animals grow faster, and some cells grow really fast. Some cells just don't grow, but differentiation is really good. Some cells grow up to 20, 25 passages, but they never differentiate. So we have to characterize every single cell that we tier them to 1, 2, 3, then choose which cell to use for proliferation testing, and then which cell to use for differentiation testing, and how we are going to choose them just by test and see how they react. That's how we approach ourselves in SeaWith.
Yeah, you want to add something?
Yeah.
Okay.
The idealist in me really likes the idea of having a common cell bank that the entire cultured meat industry can use with extremely well-characterized parental lines. Everyone can just order them and it comes. It's that's a beautiful, beautiful story and idea, but I don't think it will ever happen. And the reason is because a lot of companies have built a lot of IP around their cell line engineering, and they've spent a lot of money and time on engineering their cell lines, and then they build these biobanks, which end up being a large competitive advantage for those companies. So the idea that those companies will just open up those biobanks and let everyone use them, to me, seems unrealistic, even though I think it would be a wonderful thing for the world.
Would you still prefer to have a commercially available cell bank, although other companies will have their own cell bank? Would you still like to get cells from that then?
Yeah, but the problem will be if I take cells from that and then engineer them, who owns the IP around the cells? Who owns, how does the commercialization work? I think it would be hard to get that to work in practice, even though I think we should try.
How does the rest feel about that? Like an open cell bank?
I love it. The regulation point-wise, government cannot say anything about the source of the cell if that's well characterized. Just like in pharma, you get the COA and you get the characterization of everything. Now, if there's a universal cell line, then like an ARC, they could just develop the bioreactor specialized for that, and then everyone can use general design of that bioreactor, not specialized and then customized bioreactor. That's going to save a lot of time and money, but like Deniz said, how are we going to do that, and who will be in charge of that? Government? I don't know. Yeah.
Yeah, I guess there's a model kind of like ATCC. It's a cell bank, and they just have some material transfer agreements for what happens with IP. So I guess there's a model for how that could be done. But yeah, I just want to second that would be incredibly helpful, definitely for academia. if all these papers were referencing like the same cell line and
Yeah, exactly.
kind of compare and contrast that data and have it be more consistent, I think that would be amazing. And then obviously just like barriers to entry would just speed up a lot of things. So yeah, I think I'm a fan. I think nonprofits could, you know, lead this charge. And yeah, I think some things might be in the moves to get it set up as well.
Yeah, I think what Natalie is saying, like there's enough papers published with primary cells when if you repeat it, you actually don't get the same results. And I think many cultured meat companies can also agree that there's a lot isolation to isolation variation. And I'm actually wondering, Natalie, since you at ARC are working on a larger scale and are modeling the cell behavior as well, do you take into account that cells have this isolation to isolation variability? Like, how do you take that into account if you're modeling your system?
Yeah, I guess that's a more detailed problem, but we're just trying to, you know, make sure our system's gonna work for like cow cells and chicken and fish and like a wide range of cells. So I think we definitely want to do a lot of runs with a lot of different cell types, but the technology, you know, should be able to support, I'd say like 90% of approaches. So I think we're just designing it to be versatile. And also that's where the digital twin and the computational modeling tools comes in. No matter what cell type or, you know, batch you're using, if it's characterized to a sufficient degree at one scale, that data can be translatable to larger scales.
Right. So maybe you actually do the modulation would be good to do with a cell line because it's more reliable, and then afterwards you can make the adjustments for like primary cells, or?
So for each cell line, you'll need to do that data compilation because it'll be different for every. So we do need like a well-defined process at small scale to be able to model the large scale, and that will be very cell specific.
Right. And Deniz, how do you guys handle this?
You know, this actually touches on a larger problem, which is that even if you can model with one specific cell line, you're not modeling something that's static. So your cell lines are changing all the time. Even if you're not genetically engineering your cells are accumulating point mutations. This is pretty well characterized. They are changing over the course of your culture. So what we think about is, how do you have a system that can be monitored continuously and that can be adjusted on the fly to adapt to how the cells are adapting to the culture conditions, because that's what you're going to need, because you're not working in the static system.
Yeah. As a follow-up question on that, I don't know if you guys are already working, like submitting novel food dossiers for this. Well, I think ARC is not, but maybe Prolific Machines is.
Novel what? I didn't hear the second
Novel
word.
food dossiers to...
Photoshays.
Novel food, yeah. So when you want to get approval for bringing a novel food to the market, you have to stick to a lot of rules and regulations, as we've been talking about at this conference. And you have to stick to like good manufacturing practices. If your cells are being inconsistent and actually kind of unreliable, I was gonna ask like how do you regulate this? Like how do you handle this? Is there anyone who can give a little bit of insight on that? Is that something you guys have already have challenged?
Something that we think about at Prolific is just initially just trying to understand the problem. Like, to what extent is genetic drift happening in cells? Like, we know that they accumulate point mutations, but how much does that really matter? It's a very complicated problem, because often when people are working with a cell line, like if you do single cell RNA-seq, it actually turns out that it's like seven different populations in there. Each of those subpopulations have their own characteristics and properties, and so the situation is like far more complicated than it initially appears. Yeah.
Does anyone want to add something? No, then I think we'll make it a little bit lighter and go back to creativity. And I was actually wondering if you guys have students or peers, like how do you inspire them to be creative and get up with like new solutions to the problems that we encounter?
Yeah, I'll take this one. We did just so much work with students at Tufts. We designed a cellular agriculture course at Tufts that we've been teaching for the past few years. And at the end of every semester, we do like a Shark Tank situation. We call it Pork Tank. And students will pitch, original ideas for companies or research proposals. And I think what we've learned is really important and is actually giving some constraints and not leaving it super open-ended. I think the first couple semesters really like just come up with something novel for cultured meat. And we didn't get as creative as solutions, but I think more recently what we've done is like give them the TEAs and LCAs from the industry and like pointed them to solving one specific problem or giving them some sort of constraint, like you have to use this technology or you're in more of a box, and we've gotten a lot more creative solutions. So I think kind of pointing them in a direction is really helpful rather than leaving it open-ended, because it's easy to just kind of like, pick like a random food that someone hasn't done, but that doesn't lead to as much creativity. But yeah, I think, just like giving them resources and a focused problem to solve is really helpful.
So, sorry. So what we do in SeaWith is, that's usually me telling them is like, there's no expert in this field. Like no one ever made it cultivating meat successfully in the market yet. So, like even you're a student, you're really young, you're in high school. None of the conventional way of the growing the cell will now work in the cultivating meat because we got to make it cheaper. So, the way of using sterilized serological pipette every single time for everything might not work. Even using tea flask, that's not going to be able to make the cultivating meat. So we got to come up with a new idea, new solution. Usually what we do is like, we learn a lot from the food industry. So food industry developed a lot of machineries used for food processing that can be also transferred into cultivating meat area. So we use, like I say, we use like high-tech of low-graded version of stuff. Like for media, we are using food-graded substance. We are thinking about going into the feed grade, even lower-graded one. But that's another approach that you gotta find a cheaper way to do it, but has to work same as really high-end pharma-graded stuffs.
Yeah, so we don't quite have a cool name for it like Pork Tank, but but we essentially do the same thing. We have brainstorming sessions and we encourage our students to explore and try new things. You wouldn't believe the things some of them have decellularized. but
Can you give some examples?
What's the craziest thing someone's decellularized?
We've decellularized several flowers. I think the weirdest thing was an orange, like a whole
orange,
a whole orange,
whole orange,
the whole thing. But I don't remember why we wanted to do that. To be honest, that was a while ago. But yeah, we essentially, obviously this changes based on the cost of the experiment they want to do, but we try to keep the barrier to exploring new things kind of low. So in these brainstorming sessions, we come up with a challenge that we're trying to address, and we encourage everyone to share their ideas as far as how to solve it. And when we come up with something that's potentially viable, we go for it. So, yeah.
So what I'm hearing is really giving people space and no judgment.
And creative freedom, yeah.
Right.
I
Deniz?
think it's such an important question. It's something that I spend a huge amount of time thinking about. Is like, how do you make sure that all of your employees can be their best? And creativity is a really important part of that. I think it boils down to two things. One of them is autonomy, and the other one is trust. And I hear a lot of people, especially CEOs, talk about giving people a sense of autonomy. And there's a really nuanced but important distinction between giving people a sense of autonomy and giving people actual autonomy. A sense of autonomy is, you know, that you want to make people feel like they have autonomy, but actually you make all of the decisions, versus actual autonomy, which is you trust people to do what they think is best. And like something that I've done that has always served me well is I consistently try to hire people that are smarter than me. And if you do that, there's no point telling them what to do. Like you're spending all this time and money hiring people that are smarter than you so that they can tell you what to do. Like that's the ideal case scenario. If you're hiring people smarter than you and then you're telling them what to do, what's the point of hiring people smarter than you if you're just going to tell them what to do?
So if they are smarter than you, how do you motivate them to be creative?
You trust them. And if they really are better than you, which in the case of Prolific Machines, I'm definitely the least impressive member of Prolific Machines. Yeah, just give them the trust, autonomy, and resources that they need.
All right, sounds good. I have a question for you guys, and I hope that you guys want to share, if you can actually remember this. I was wondering, what is a creative idea that you tried and actually failed horribly? Because we all learn from mistakes, right?
I could start on that. So I just talked about we use a lot of food industry stuff. Making large centrifuge, they are very, very expensive. So what we came up with the idea is use, have you ever seen how farmers collecting the honey from the honeycombs? So they use a centrifugal force to extract the honey out from the honeycombs. So what we just bought it and thought it's going to be a great idea, and it was like $500 for like whole machine. It was really cheap. Yeah, it's close to nothing compared to any centrifuge like in your lab scale. Like any of them will be like more than $500. So we bought it and then we spun it. The problem is it's not well made once. So the center bar was shaking, so that like we weren't able to use it. But we have an engineer in our lab. He enforced it, and it works quite okay. But you ended up not using it. So that's something that like we try is, if there's a similar function that out there, we just buy it and then try it, or we contact the manufacturer and saying, we want to use it for this reason. Can you go to your factory and then try it on? And can you make this modification? Even if you make the custom equipment, it's going to be way cheaper than regular laboratory stuff. Yeah.
Thank you for sharing. Anyone else has anything to share?
I can share a story from the early days of Prolific. So, as you know, we don't have this centralized biobank where everyone can just go and say, I want this cell line. So one of the first things that I did at Prolific, this was before we had like real employees, I tried to derive some Wagyu stem cells. And the first step to trying to do this was I Googled like Wagyu stem cell isolation, and there was nothing, because like there were no papers on Wagyu stem cells. So I was like, fuck, what am I gonna do? I had a lot of experience from my PhD and previous work on the liver and human liver isolation. So I was like, I wonder if I just like do what I used to do for the liver with some like Wagyu muscle and fat, if I get some stem cells that are useful. And so I did that, and I was like, oh, nice, I got some stem cells. These look pretty good. And then we hired people who were much smarter than me, and then they came in and they were like, Deniz, the hell did you do? Like, these are not muscle stem cells. So we had to rederive all of our cell lines.
Any idea what kind of cells they were?
They were probably fibroblasts.
Okay. That's still be useful.
Still useful as a control.
Thanks.
In the earlier days of our research, we were looking at how to scale up the scaffold production. And at the time, our decellularization method was it was cannulation based. So essentially you would cannulate the stem and you would perfuse the decellularization agents through the leaf. We have since gone to more of a vat style, like I said, where the leaves are submerged in the decellularization agents. But at the time we were trying to scale up the cannulation process. So we did it. Long story short, we did it successfully. We created this large apparatus that had an array of leaves that are all cannulated and had the decellularization agents flowing through all the leaves successfully. But one thing we didn't account for was that the agents that we used would also break down adhesives. So after we started decellularizing this large batch of leaves, the thing starts to like break down, and like the liquids are like pouring all over the counter. Definitely an experience we learned from, but yeah, that's pretty much it.
Yeah, definitely a mistake you learned from.
Yeah,
Maybe.
definitely something we learned from that.
Yeah.
Yeah?
Share a story. We've been fabricating like scale down models of our bioreactor, and to make like the perfect version, I guess we would have had to like wait a couple weeks for certain parts to come in, and we wanted to just like get it up and running. So we ended up, we have this awesome rapid prototyping team that is amazing, and they just kind of like more scrappily like put something together with like 3D printing and a bunch of different materials, and we were really excited about it, but didn't really have time to like make sure everything would actually survive the autoclave. And so much time went into like creating this awesome little reactor, and then, you know, you put it in the autoclave and like the door slowly goes up and you're like, bye, see you in a couple hours. And then when the door came back down, it just like completely warped. But still worth the effort, and, you know, just being creative to put something together to save time. But yeah.
We had the same experience.
I've accidentally melted my fair share of things in the autoclave. You're not alone.
I think more people can relate to this, right? I think everyone has probably at one point melted something in the autoclave.
It's not always clear what is and isn't autoclavable.
It is. And you can always try, right? You can always try. Just put it in.
It looks autoclavable. It's like, oh, fuck.
All right. I'm going to ask one last question, and then we will have time to take questions from the audience. So if people want to line up at the mic already, then go ahead. So my last question, guys, is in hindsight, now working in this field for a couple of years already, is there a skill that you would actually want to have before you entered this field? Is there anything that you would have greatly benefited from?
Yeah, I've always wanted to have a stronger background in like meat science. I try to do like some reading, you know, here and there, but I really wish I had like a super strong fundamental. Like, I think the most impactful conference I probably ever went to was like the National Meat Science Conference. Me and Andrew went and gave a presentation, but everything, like, we learned so much, and it really changed, you know, how we address things in the future. So I wish I had done some more food science, meat science.
How did it change how you address things? Like, what aspect really opened your eyes in that sense?
Just like the questions we got from that community, I think were the most insightful. Like, I remember we were talking about sterility and production, and we had a lot of questions saying, well, there's like good bacteria in meat too. Like, maybe you don't want it to be completely free of, you know, any microbes, and we had never thought about that before. So just a lot of, you know, insights from that perspective that we just wouldn't know to think about.
Did you look into that more? Like, did you find any bacteria that we can actually have in our culture without messing it up?
I did not specifically look into that, but I think some people are.
Yeah, that's where the meat science knowledge would come in handy. Yeah. Anyone else want to add something?
I mean, the list of things that I should have had before starting this is long, and it will take up the rest of the conference if I was to go through it. But I think something that something that I've learned is, I think the key challenge with any startup is, especially in biotech, is you have to have a sense of urgency and move quickly, but you also have to not build a house of cards. And those two things are somewhat opposing, because you want to go quickly, but often the way to go quickly is to cut corners, and if you do that, you're going to have to end up redoing all of your work. So I think this is like the eternal balance that has like become very clear to me recently, but was not totally clear to me at the start. At the start, I was like, let's just go quickly, let's do it, and then we ended up just having to redo a lot of that work. Whereas really keeping in mind that you have to build really solid foundations, and sometimes going slower, it feels like you're not making as much progress in the short term, but you're actually going faster in the long term because you're building on really solid foundations. That has become clear to me, but was not. It's like a hard lesson that you have to learn sometimes.
Yeah, we had the same experience too. So we decided to do something really fast, like within like 6 months or something, and then everyone thought it was possible, but everyone here did their research, so nothing goes on your plan. So we ended up replanning everything from the very ground of technology like that we developed back up almost like twice already. So sometimes like going slower, getting all the basic technology built up first and then moving up to the next level could be the faster way than let's finish this within like 1 year or something. Just instead of setting the time point, I think your goal, like the milestone, will be more like suitable in this field, I guess. Yeah.
The thing to appreciate is that it's easy to do either of those things in isolation. It's easy to be really rigorous if you don't give a shit about going quickly. And it's really easy to go quickly if you don't give a shit about being rigorous. The hard part is trying to do both.
Yeah, I think one of the things that I wish I would have learned earlier was learning to talk to the customer or your perceived customer. At the time, when I first started, I went about it really scientifically, right? I had these goals, I had these parameters, you know, these are ways that I'm going to address those parameters to develop this product. But then I participated in NSF I-Core. I don't know if anyone else has participated, but it's essentially a program that teaches you customer discovery, where you go around and you talk to your perceived customers and you ask them questions, non-leading questions obviously, about different aspects of your product that you want to improve. And you'd be very surprised at the answers. The answers that I would get back, I had no idea that that's where their mind was as far as the product. And I didn't realize how important that is in the beginning, like of deciding how you're going to tackle this problem. And it's something I wish I had known earlier, to talk more to my perceived customers to reevaluate the approach. So.
Do you have any examples of how the customer surprised you?
Let's see. That was a while ago. I think one of the things that I didn't originally take into account when I was going through the culture meat process, because I was very focused on, okay, how do we isolate the cells? How do we make them proliferate quickly? How do we differentiate them? That's where my mind was. And then I went to go speak to the manager at a restaurant, and they were like, okay, well, what will it look like? Like, how brown will it be? Will it be like a dark brown, light brown? And I didn't think that far. I didn't think that far ahead yet. But these are all, like, the way it looks is very important. The way it smells is very important. And those are not things I initially thought about, and I wish I had known to think about those characteristics sooner.
Yeah, thank you. All right, I think we will take some questions from the audience. So I think I see a queue. Yeah, go ahead.
Thank you all so much for this. It was really insightful. In this panel, it's like you just shared all these amazing things. So Lily Yang, the Andriessen Group. So just kind of wondering, when we are thinking about all this IP that you're talking about, right? We're talking about like cell culture lines, developing new technologies, new bioreactors. And then in that sense, right, everybody even here in this room, fairly siloed off doing all this. And yet yesterday, you know, part of that discussion was like, how can we be more collaborative? I think Justin was the keynote saying we need to be collaborating more together. And as we talk through all the science communication, we should all be collaborating more together. So how do you all find yourself juggling this liminal space, and what is yours versus what can be the collective whole, and what you're willing to share, if you're willing to share, and what would move you to share and collaborate more?
I could answer that. We do a lot of collaboration with other companies. So initial thing is NDA. So instead of teaching them technology, like we could provide our scaffold of that we have, we are willing to share that with other company. So we've been shared that scaffold with some crustacean cell line, sheep, pork, beef. Even though we do beef, we just share our product to them. If one company could succeed with our product, then we're happy with it. And they could be a future customer on our B2B strategy. And it is also a proof of concept that our scaffold could work in any kind of cell line, that we have a large portfolio of like which type of cell was working well. So if anyone wants to try our scaffold, just contact me. I could share that with you.
Yeah, really good question. When I was leaving my PhD program, like I knew how much I was going to miss the collaboration. Like I loved that so much. So I was really intentional about looking for companies that had, were focused on one aspect of the technology. So I really wanted to join like a B2B, and a huge reason of why I joined ARC, because I just knew like we're designing something that we want the other companies to use, so we have to be collaborative from day one. And then it's really clear what our incentives are. Like we care about bioreactors, we do not care about, IP around cells and media and scaffolds. And so that's allowed us to be super collaborative, and we work with, companies on cells and media and scaffolds. And it's great because they want to, show that their systems work with our system, and we want to show that our system works with their system. So it's been really collaborative, and it hasn't been as tricky around IP as I was worried about.
I think it's a really important question. I kind of alluded to my views earlier, which is that I think collaboration is really important, but it's going to be very difficult, especially with competing direct-to-consumer companies that have spent a lot of time and invested money on building a particular technology that capitalism will not incentivize them to share. And so I think what's the right thing to think about is, what are the avenues where we share common problems and collaborate on those? For example, like regulating the Farm Bill in 2023 is clearly like something that's going to impact every cultured meat company. We share a common interest. Like, there are people on the other side of the table, like the American Cattlemen's Association and other cattlemen's associations worldwide, that are collaborating to try and make this very difficult for cultured meat companies. So I think it makes a ton of sense for cultured meat companies to collaborate there, try and get a favorable Farm Bill in 2023. On the science itself, I think I'm more optimistic that the academic sources will be the source of collaboration. Like, I really like what New Harvest is doing. I really like what the Good Food Institute is doing. I think, the more I'd love to support them in any way I can. So if you're in those organizations, you can come talk to me afterwards.
Yeah, I agree with what everyone has said. I guess the only thing I'll add is that I think the challenge that we're trying to address here is huge, and as such, I don't think it's wise to go about it as, an individual. Instead, you should look to others who have made significant progress in one area. For instance, you should partner with someone who has a working or close to working serum replacement, for instance, or maybe partner with someone else who has a functioning bioreactor designed for scaling up satellite cell proliferation, things of that sort. And I think that's kind of the form we're going to see cultured meat come to the market in. It won't be one large entity that has figured everything out. I don't think that's the way to go about it. I think it will be a series of partnerships. So,
Thank you.
Hello, I'm Dr. Aveli Salinas, and I work at Mission Barnes as a bioprocess engineer. The question I want to ask, I've asked in like different spaces before, like the medical device industry and like cell therapies and stuff like that. And it's about isolation to isolation variability, which you guys touched on a little bit. Do you think pulling cells from multiple donors of the same species for creating cell lines and cell banks would reduce variability in product outcomes overall? And can you perhaps explore the pros and cons of pulling multiple donors over a single, like perhaps super donor? And this question, I guess, goes to anybody who would like to answer.
Probably that's question to me, which is we got from like 30 different animals. So that's a tricky question. We are getting it from multiple donors because we don't know what will be the good answer to that. That's why we are testing, characterizing every single donor. And also you're saying a super donor, the difference will be when you're taking the tissue out of it. You're doing the biopsy. So age of 5 months will be totally different to 2-year-old super donor. So that won't be the optimal way to do it. I think if you want to get the tissue from one donor, then that's the one characterization. If you get the same sample, try to get same sample after like 6 months, the cell will not be same.
Yeah, I think something like a cell bank would be very, I think it's required in my personal opinion, and the reason for that is for isolation variability. Not only does it differ between species, but it also differs between different areas. Like, you know, if you have a cow in the United States, for instance, the cells may behave very differently from a cow in Europe, for instance. And then on top of that, like you touched on, age plays a big part into it as well, and as well as where the sample is taken on the animal. So I think these practices need to be standardized, and I think the best way to do that is with something like a cell bank, where you raise the cows in a certain way, a very standardized way, and you take the samples from the same area at the same age, so on and so forth.
I completely agree. I agree with that. I think there's a lot of value in taking lots of samples from lots of different animals when you don't know what you're doing and you don't know which is the right place, what's the right age, what's the right protocol to isolate those cells. But ideally, you know, to get to a price point to compete with factory farming, I believe that you have to immortalize the cells, and you probably have to do other genetic engineering to the cells. And for that, you're going to have a master. I know that you disagree, but with, you know, some companies aren't doing that. But I think I'm pro genetic engineering. So for that, you're going to have one master cell bank eventually that is extremely well characterized and immortalized. And once you have that, you don't need the cows anymore or whatever animal.
Thank you. This was a great panel.
Hi, my name is Chris, and I was curious about, as things begin to scale up, what potential there is for automation in the manufacturing process, and like what % of the process could be automated, and whether you guys see that as a solution to contamination.
Yeah, definitely. Huge opportunity for automation. That's definitely been part of our approach from day one. Automation engineers, some of our early hires, and I think that'll be like absolutely critical for bringing down OpEx. I think as someone alluded to earlier, it takes like a really large amount of people to like operate bioreactors right now, and that won't be scalable and isn't good for sterility or cost. So yeah, for sure.
I completely agree. I think there's no world in which these factories are going to be managed by scientists. Like, scientists don't scale very well, especially in the Bay Area. Some of my employees are here. They know how much they get paid. Yeah, automation is going to be essential. A large part, like the meta point with Prolific is like teaching machines how to grow cells. And so like one of my co-founders is a machine learning engineer. Like we have a software team. It's going to be essential.
Yeah, I agree with all of that, but I'm glad you asked the question because I differ a little bit in that I don't envision a world where we completely eliminate, farming completely. I don't think that that's the good way to go about it. I think it's important that we don't lose touch with our agricultural industry. These are our experts. They've been raising these animals, as forever, right? And I think they are an important part of this as well. We don't want to alienate the current agricultural industry and instead work with them. So, maybe we have much smaller herds, right? Because we don't need to raise enormous numbers of animals, but instead we have, smaller herds with experts raising them properly with the right food and everything. So I don't think that part will be automated ever, but definitely downstream from that, there's definitely lots of room for automation.
Thank you.
Hey, great panel. Amit Khan from Cell Agri. In coming up with creative solutions to address scaling up production, what role do you see partnerships and collaborations with traditional food or even biotech and pharma players in helping scaling up the field?
Like their know-how of operating large-scale factory-like processing. So that's going to be a lot of stuff that we need to learn, not only the technology-wise, the safety-wise. Like mentioned earlier, it was steaming, or sometimes people might use radiation or some sort of way to sterilize. That's going to be a big hazard for workers to be involved, and none of our team is trained to do that. So that's going to be a big thing. Every single type of regulatory procedure within the company will be the big thing. Another part is logistics. Some team worries about the logistic, but we have it's not non-binding, it's not even the MOU or anything. We have some talk with the distributor who has large supply chain within Korea. So they say they're a food company. They're not going to make the cultivated meat, but they willing to sell it for us. So if you have some connection with that, and you don't even have to worry about the logistics, just make your product and give it to them, and they'll sell it for you.
Yeah, and I think partnerships are going to be important, especially with the established agricultural industry. Even if Prolific is successful and we can eliminate the recombinant proteins and growth factors, for example, we still need glucose, we still need amino acids. Those will need to come from somewhere. And I think the best source for them is likely partnering with agricultural players that have a lot of plant waste that we could reutilize. That's just one example. There are probably other examples where it makes a lot of sense to partner with existing agricultural players. It also makes our case a lot stronger when we're going to US senators and telling them that they should look at cultured meat favorably for the 2023 Farm Bill. I recently was at the Breakthrough Energy Ventures Summit. I was speaking to a member of Congress, and I was how do we make sure that cultured meat isn't completely fucked by the Farm Bill? And he was like, you should be worried about this. And I think one way that we can do that is by highlighting how cultured meat can help existing farmers. And I think the glucose amino acid argument is a sound one.
Thank you.
Hi, I'm Kiki from Wildtype. I wanted to think of a fun question that could maybe test your on-the-spot creativity. Natalie, you might hate this one, but if you couldn't use bioreactors, how else would you scale up the cells to an amount that we could actually use in the market?
Interesting question. I think they need a second to think about it. Anyone want to? Oh, yeah.
Scale up. I don't know about the scale up, but I know there's a undergrad researcher group growing their cell in Tupperware.
Tupperware.
Yeah.
Can you give us some more details on that? Or
They just put media and cell inside of the Tupperware.
That's it.
That's it.
All right.
And they don't even have an incubator. They have so temperature regulator that just put Tupperware in, and then cells grow
Very
pretty well.
interesting.
Do you know which species they're growing?
They do crustacean, and they grow pretty well in that condition.
I guess I would say that is a bioreactor. Like, I think.
Yeah,
I guess I
basically
would-
it is.
Yeah, I think a bioreactor doesn't have to be like a cylindrical stainless steel tank. Anything that's maintaining sterility and manipulating conditions is a bioreactor.
And they use microwave to sterilize.
How do they supply oxygen?
You get the CO2 tank and just put it in.
A what?
Connect with
So
tube
they
and
just
then
made a
just put it
really
in.
cheap
Right.
bioreactor.
Yeah, very cheap bioreactor.
You could do it at your home if you want to.
Yeah.
What about stirring? What about the stirring? Are you just like some poor grad
know.
students just like...
Yeah, time to time they just take out and stir. Probably you could put a stir plate. So
Yeah, magnetic stirrer in there.
that's pretty cheap. So,
Oh, I have a good answer. I was talking to someone from Tufts about this the other day. We have body temperature, so you could just like kind of hold it to keep it warm.
All day.
I feel like the obvious answer is 2D, like growing cells in 2D instead of like 3D reactors. The problem, of course, is that 2D cultures don't scale very well because you end up needing a huge amount of space, and space is expensive, and then you can't compete with factory farming.
Yeah, you mean just layering up then? Layer by layer. By layer.
Yeah. So people have proposed these like 2D solutions, and I haven't been convinced by any of them. I think going into suspension makes a ton of sense from like a cost per square inch perspective.
Yeah, I agree. The obvious, right? I know you're trying to be fun, but
Well, it's called Let's Get Creative, so I thought.
Yeah. So like you said, the obvious answer is to go to 2D, and you could get creative and take that and maybe use different shapes or different forms. Like Natalie said, a bioreactor isn't necessarily a stir tank reactor that's stainless steel. It can come in different forms, like hollow fiber. There are some what are they called? Rolling tank.
IKEA Tupperware.
IKEA Tupperware. Yeah, but they come in all different kinds of forms, and I think this question is more so like, how do you be creative with making a different kind of bioreactor? And I have a few, like one idea that I had a while ago was that I had like a drum, right? And the cells would live on the inside surface of this drum, and the drum would spin. And this was kind of a way to minimize the amount of media that you need, because as the cells are rotating on the inside surface, they would eventually go into the media, and that's how they received the nutrients. And you could kind of like try to scale that up by maybe having concentric these drums like inside one another in kind of a concentric way. So that's one idea I played with a few years ago. But that's, like I said, just a different bioreactor design that looks at 2D instead of 3D.
Also, there's a special coating that it changes the charge by the temperature. So if you just lower the temperature, cell will detach from the surface. That way, it could be possible to scale up in 2D, I guess.
Cool, thanks.
That was a really nice question. Thank you. I think we have one more. Can we? Yep.
I have a question for Natalie. So you were mentioning insect cells. Do you ever see like how far in the future would you ever put a date on selling insect cultured meat?
Yeah, I think there's like a consumer answer versus a technical answer. Technically, insect cells are a lot easier to grow than other cell types, which is why I was working on it for my dissertation. They don't need growth factors. They grow at room temperature. Other industries have already scaled insect cells to, really, really large volumes for like the therapeutic space. So there's a lot we know about them. And that you can insects have muscle and fat, so you can create meat analogs with them. So technically, it's probably easier than other species, but I don't necessarily think insect cultured meat products should maybe be the first batch on the market. I never really cracked the code of how to communicate it succinctly and effectively to people, so maybe we need some creativity from marketing to kind of communicate that. But like maybe for pet food or some of these other ancillary markets people talked about, it could be an interesting path forward.
You know, cockroach burgers, why is that so hard?
Sounds delicious.
So economically speaking, do you think that cost could ever, because insects are really cheap to grow, just like by themselves, do you think that the cost parity will ever be achieved?
Yeah, good question. So I don't really compare like growing insect cells for cultured meat to edible insects because the products are not the same, so you can't get anything that tastes like meat from edible insects. It's just like there's, you know, if you think about like crickets or whatever, like there's very little muscle and fat, so by targeting those tissues, we can actually make something that looks like meat or seafood. But I've, you know, talked a lot about this and gotten a lot of input from actually like the insect farming community, and it's a little less scalable than I thought it was. There actually are a lot of issues with scaling insect farming. There's a lot of disease, and insects actually like eat each other if they're farmed in close quarters. So I've actually been approached by people from the insect farming community that are actually pretty interested in this.
Thank you.
All right, then we're going to wrap this up. I want to thank everyone on this panel. Very nice answers, very nice new insights, and let's give it up.